I'm Carl Fisher with Thermo Fisher Scientific, and today I'm going to be talking to you about sample concentration and analysis of hormones in drinking water. You're probably wondering, why would you be interested in hormones in drinking water? Well, there are a number of reasons. As you can see here, there have been pharmaceutical residues that have been found in our water supplies. In 2008, the U.S. Geological Survey tested tap water in 9 different states across the country, and they found 85 man-made chemicals, including some medications. Additionally, many research centers and a number of news outlets have reported traces of various pharmaceuticals, including antibiotics, anticonvulsants, mood stabilizers, and synthetic hormones. How do hormones get into drinking water? There are a number of pathways that this can be happening by. You can see that the home is a primary source because people are going to be taking contraceptives and, say, perhaps they're taking hormone replacement therapy. And typically, once they've done with that therapy, they may want to dispose of their medication somehow. A lot of times they'll just dump it down the toilet, or they may excrete some of these, and eventually it's going to end up in your wastewater treatment facility. Down below on the bottom of this slide, you can see EE2. So that is an oral contraceptive. That's ethinyl estradiol. And that is a major concern because a lot of people are using contraceptives. So you can see wastewater treatment is there just below industry and home, but hormones can also come from landfills. So you can see on the right-hand side, if people improperly dispose of their drugs, their medications, then they'll just be putting them in the trash, and eventually it may leach into the groundwater. Additionally, agriculture and other things such as livestock themselves have a lot of hormones. So they're going to be secreting those, and it's going to eventually make its way into the water system. So either surface water or groundwater, and eventually that may be treated for drinking with various means, and eventually it may end up in our drinking water. There are a number of health risks associated with hormones in water. Even at very low concentrations, you can have impacts on aquatic life, such as freshwater fish. There are also some long-term consequences, particularly in humans, because cancers are known to be hormone responsive. They can also impact male fertility, leading to infertility. There has been a link between sperm count and estrogens in water. And we're not really sure what's going to happen in humans, but likely there is going to be some link there. Obesity, weight gain has been linked to rising estrogen levels. There's also the stew effect, so there may be a lot of synergism happening that we don't know what the impact of that is. So a lot of things combining, and what the outcome of that is, we don't really know. So it's really a concern for people. In 2010, the US EPA came up with Method 539. And this essentially looks at hormones in drinking water using solid phase extraction and liquid chromatography, electrospray, ionization, tandem mass spectrometry. It's quite the mouthful, but it's a very powerful technique. In 2012, the EPA signed the third Unregulated Contaminant Monitoring Rule, so UCMR3, and this requires the monitoring of 30 different contaminants using EPA or consensus organization analytical methods. So these are standards that have been agreed upon, and they're looking at these things. They started in 2013, and they're looking all the way through to the end of this year. So as I said, there's about 28 chemicals and 2 viruses that they're looking at. So there's actually a broad spectrum of things that they're analyzing. And at the end of 2015, at the beginning of 2016, they're going to look at all of this data and decide which ones of this 30 they want to actually create regulations for and set limits. US EPA Method 539 is included in UCMR3, and down below you see that these are all of the hormones that are monitored for this method. I've listed here the hormones. You can see that in red, boxed in red, are the estrogens. So these are the human hormones: estriol, estrone, and beta-estradiol. In blue, I have the androgens, testosterone and androstenedione. Down below, you see, just by themselves, you see ethinyl estradiol, so that's the EE2 that I showed you earlier, and that is a synthetic hormone. And that's, as I mentioned earlier, it's an oral contraceptive. There's also equilin that's used for hormone replacement therapy, and that actually comes from horses. Testosterone, well, that's also used for hormone replacement, so that's why you might see it in the waters. And androstenedione, you probably won't see it too much anymore because I believe in 2004 the FDA banned that because it's a performance-enhancing anabolic steroid. So this is a whole set of 7 different hormones that I'm going to be talking to you today about. So these are the tools that I've used to collect the data that I'm going to be talking about. So on the left-hand side, we see SPE, so that's solid phase extraction. And I'm going to be using the Thermo Scientific Dionex Auto Trace 280 solid phase extraction instrument. And this is going to be using Dionex Solex SPE HRPHS cartridges. And I'll talk more about each of these individual components in a few minutes. So from that, the extraction is put onto an LC-ESI-MS system. So the LC part of it, the HPLC, is a Thermo Scientific Dionex Ultimate 3000 LC system. And that is then paired to a Thermo Scientific TSQ Quantiva triple quad mass spectrometer. Right, so if I'm focusing here on the Dionex Auto Trace 280, you can see that it actually can use a large volume and concentrate that down. So from 20 mils all the way up to 4 liters of sample, you can concentrate down. So typically this uses drinking water or groundwater, and it applies positive pressure to push it through the cartridges. Primarily it's used for sample prep for organic analytes such as organic pollutants, personal care products, endocrine disruptors, and of course the hormones that I'm going to be talking to you today about. So this is an automated system. It fully automates all of the steps: conditioning, loading, rinsing, and elution. And you can use normal or reverse phase cartridges or even discs. And they come in various sizes depending on your needs. So 1 mil, 3 mil, and 6 mil SPE cartridges. So this essentially is going to save you time and solvent and will give you good reproducibility and great precision. Here I'm focusing on the SPE cartridges themselves. So these are Solex cartridges. They have a number of bases. So either they're silica-based, carbon-based, or polymer-based. The one I'm going to be using today is a polymer-based one, and it's the HRPHS. And that is a hydrophobic, reverse phase, high surface area cartridge. And the size that I'm using is 6 mil with 200 milligrams of resin. So now I'm going to be taking you through the sample prep using SPE. So we're going to start off with 1 liter of water, and it's going to have a biocide in there, something to remove the chlorine because that could interfere with your analyses, and then a mass spec surrogate. The surrogate I'm using here is bisphenol A, so BPA, and also I'm going to add some hormones to it. The reason I'm adding a surrogate is because I want to be able to monitor the performance of the extraction. I should have the same amount that I added at the end so that it's going to verify whether or not I lost anything along the way. And you certainly don't want to lose anything. So that's why the surrogate is present. And this is just an image of what the surrogate looks like. And you can see the structures, it's not exactly the same as the hormones, but it's got a very similar characteristic. So this is what you want in a surrogate. So this is the AutoTrace itself. So this 1 liter is actually loaded onto this system, and you can see there's 6 positions for cartridges. As I said, all of these steps are automated. First, we're going to start off with conditioning using methanol, then water, followed by nitrogen. We're going to load 10 mils at 10 mils per minute, and then do a rinse step. So I'm going to take 10 mils of 15% methanol, add it to the bottle, swirl it around, and then I'm going to load that onto the cartridges. And then finally, once I'm going to have about 10 mils that's going to be eluting off of here. Actually, just prior to that, I'm going to dry it with nitrogen, make sure I get most of the water off of it, and then I'm going to do my elution. And the elution is going to be in multiple steps. It's going to be 2 steps of 3 mils, and then finally a 4 mil step. And this is going to make sure that I get as much off of there as I can. Hopefully, I should be getting pretty much everything off of there. And that will be confirmed when I look at my MS surrogate. So once I have approximately 10 mils, I'm going to actually dry it down using nitrogen. And this is going to be at 45 degrees C. At that point, I add approximately a mil, and I say a mil because it's going to be composed of, with the work that I did, I actually added 990 microliters of methanol, and then 10 microliters containing my mass spec internal standards. And the standards are composed of estriol, estradiol, ethanol estradiol, and testosterone. And these are either deuterated or carbon-13 labeled. And the reason I'm adding these is because these internal standards can help you determine whether or not your HPLC injection is working properly, or whether your mass spec ionization is efficient or not. And you can actually adjust for that based on the performance of these MS standards. So that's my preparation of sample. From there, I go to my HPLC system, and it's an Ultimate 3000 RSLC system, and it's got the typical components for an HPLC system. You've got a degasser, you've got your dual gradient pump, thermostated auto sampler, and then the thermostated column compartment. For the samples, I kept them at 4 degrees, and that's a typical temperature that one would be using. Inside the column compartment, I have an Acclaim rapid separation LC column, so a Polar Advantage 2 column, and it has a nice small particle size, 2.2 microns, and then 2.1 by 150 millimeter in size. The reason I chose this was because it has a high tolerance for pH. It can go from 1.5 all the way to 10, and the buffers that I'm using here actually have a very acidic pH, so it's around 9.6. So this is a column that's able to tolerate that. Here are the HPLC conditions, and you can see that I injected 50 microliters, and that's standard for the method. And the temperature of the column was 25 degrees C. The mobile phase A was water with 0.02% ammonium hydroxide. The ammonium hydroxide is added to help with the ionization of the, once you get to the mass spec side of things. The mobile phase B is 50% methanol acetonitrile, so it's just a blend, once again with that ammonium hydroxide present. The flow rate is going to be 350 microliters per minute. Down below I have the gradients, and you can see the percentage B, 20%, going up to 60, and then finally to 90 just to clean everything off the column, and then once again back to 20%. So from there we took our sample and put it onto the triple stage quadrupole Quantiva mass spectrometer. It has attogram sensitivity, and for those of you who may have forgotten your SI numbers, that's actually 10 to the minus 18, so it's very sensitive. It employs thermoscientific active ion management. It's got ultra-fast selected reaction monitoring. So what's ultra-fast? Well, that's actually 500 SRM per second, so it's really fast. You've got enhanced usability, so intuitive drag-and-drop method editor software. You've got the IonMax NG ion source, so this means that your gas and your electrical connections are automatic, so you can rely on consistent performance. You've got increased productivity. So you've got application-specific software, you've got TraceFinder, which provides a great variety of SRM parameters that you can use, and it's got a very extensive database of this. So it makes things a lot easier as far as setting up your mass spec, and it gives you a foundation, a baseline for starting. Here are the mass spectrometry conditions. We have heated electrospray ionization, so HESI-3. Various spray voltages depending on whether or not you're using negative or positive mode. I'm actually using both with this particular method. You have the various gas pressures, ion transfer, capillary temperature as indicated, vaporizer temperature, the scan type. So we're doing selected reaction monitoring. So we're actually looking at particular product ions that have been fractionated from precursors. So we're just looking at precise ions. We're not looking at a whole spectrum of ions. So the data you're looking at is much narrower, and you're just looking at specific retention times. The Q1 and Q3 peak width, so this is full width half maximum, is 0.7 Daltons. And then the collision gas and pressure is argon at 1.5 millitorr. So here you can see the ESI-MS mass transitions. We've got our compounds listed here in this one column. And I've indicated the BPA, so this is my mass spec surrogate here. And there are the internal standards in red. You can see estriol, ethinyl estradiol, and testosterone. And if you compare those to the other one, so the very top you see estriol and then estriol D2, you can see that the precursor ions are different in size, and this is to be expected. And then the product ions may or may not be the same. On the right-hand side of that, you see the collision energy that was used, so we have various voltages and the radio frequency lens voltages. And as I mentioned earlier, we have both positive and minus and negative mode that we're using. So for the majority of them, for almost all of them, we're using negative mode. And then for the male hormones, androstenedione, testosterone, we're using positive. So now I'm going to show you some of the chromatography. And you can see here, starting off with estriol, you can see that the retention time for estriol, labeled and unlabeled, is exactly the same. Below that, we see androstenedione, and then our surrogate, BPA. And finally, testosterone, unlabeled and labeled. And once again, you can see those two are right on top of each other. I've indicated here, once again, our labeled internal standards and our BPA. So the BPA, you really don't need to worry about it too much because BPA is measured in negative mode, whereas these other ones are in positive mode. So even though it looks like it's close, it's not going to be an issue. Here are the rest of them, so equilin, estrone, estradiol, so both labeled and unlabeled. Once again, these are pretty much bang on top of each other as far as retention time. And the ethinyl estradiol, once again, you can see that they're right on top of each other. So that's exactly what you would be expecting. And you can see that the peak shape is very nice, very, very symmetrical, nice and sharp, and there's not really anything else that interferes with it or gets in the way of any sort of quantification you might be doing. And speaking of quantification, you can see here's a standard curve. Of course, we have to do a series of dilutions of our standards. And to that solution, you're going to be adding not only your hormones, but also the surrogate at the same concentration used for the extraction, along with the internal standards, once again at the same concentration. So these are checks. Once again, surrogate, internal standards, these are checks. You want to make sure that you have the exact same concentration in all of your samples. As you can see here, we've got a nice straight linear line. We've got an R-square of 0.996, and this is for androstenedione, dione, and the range of concentration was from 0.02 to 20 micrograms per liter. So very nice, very good standard curve here. And all of them were look essentially like this, so we had pretty high R-squares for all of them. So now we're gonna look at some of the recovery. And I don't have it here, but for the BPA, it was about 89 to 104% recovery. So it's actually very good. And the EPA method says you can have plus or minus 30%, so this is well within that range. And you can see these numbers here on the right-hand side, the recoveries, the percentage, they're also quite good and well within the range. So what about detection limits? That's usually what a lot of people want to know. How good is this method? You can see the amount fortified in this column, the second column there. And I guess I should point out too that you can see nanograms per microliter. Previously, I was showing you micrograms per liter, and that was with my calibration curve. And the thing is that at this point, you have to take into consideration that concentration you've done, because you took the 1,000 liters and went all the way down to 1 mil. So that's how you get down to your nanogram per liter level. So you can see this is a fortified column here. And in the third column, you see the EPA concentration. So these are the concentrations that were specified, outlined in EPA Method 539. And you can see on the right of that, these are the values that I was able to calculate using the method that I just spoke to you about. And you can see that all of them are actually at or below, and some of them considerably below, the EPA indicated values. So as you can see, this method lets you get into really low MDL ranges from 0.01 all the way down to 0.12. It's okay if I do this right, because you're going to cut it out?
Absolutely.
All right, okay. So at this point, I'd like to conclude and just kind of wrap things up. As I talked about today, you can use solid phase extraction, taking it to HPLC, and finally going to triple quadruple MS. And I've indicated the various systems that I use, the AutoTrace 280, the Ultimate 3000 LC system, and the TSQ Quantiva MS system. So I was able to show you that you could concentrate hormones and get approximately 100% recovery. We've got well-differentiated MS peaks, and we're actually not just low, but we've got sub-nanogram per liter MDLs. So today I was able to show you how you can use solid phase extraction and then take that to HPLC and finally get quantification using triple quad MS. I started off with the Thermo Scientific Dionex Auto Trace 280, then I went to the Thermo Scientific Ultimate 3000 and the Thermo Scientific TSQ Quantiva MS system. I showed you that you could get approximately 100% recovery. I showed you well-differentiated MS peaks and not just low, but sub-nanogram per liter MDLs. Before I finish, I just wanted to wrap up talking about our full line of sample prep products. We have our ACE system, so Thermo Scientific Dionex ACE 150 and 350. The ACE if you only have a small throughput, but if you have large throughput, say up to 24 samples that you want to just set up in a carousel and let it go and do its thing, then you've got the 350 there. So these are for solids and semi-solid samples. I talked about the Thermo Scientific Dionex Auto Trace 280, the SPE Cartridges, and then finally there's the Thermo Scientific Dionex Rocket Evaporator. And this is for situations where you have, say, from 40 mils all the way up to 450 mils, and you want to concentrate that down pretty much all the way down to dryness if that's what you need. So this is our complete line of sample prep products. Thank you for your time.